Good morning, or afternoon, as the case may be. My name is Jeanne Chambers, and I'm the Great Basin Science Delivery Project Coordinator. Welcome to our final webinar of our Winter 11, Spring 12 series, titled Understanding Resistance to Invasion and Resilience to Disturbance, Importance for Restoring and Managing Great Basin Rangelands, presented today by Jeanne Chambers from the USDA Forest Service Rocky Mountain Research Station. Before we begin, I would like to let you know that although this is the final webinar of the Science Delivery Series this season, we will be hosting a webinar option for the Sage Step Managers Workshop in Boise on May 17th for those folks who had to cancel or otherwise can't make it due to new travel restrictions. Also, I will continue to forward webinars of interest from other groups. If you have questions during the presentation today, you may type them into the question pane in your control panel at any time, and I can respond to you throughout the presentation. I will field questions for Jeanne Chambers after the presentation. Tomorrow, the GoToWebinar system will automatically send you a link to the recording of this webinar, which will also be posted on our website. Please feel free to email or call me anytime with additional questions or comments. Sometimes, I just want to let you know that sometimes during the Q&A portion of the webinars, the sound begins to cut in and out. I'm not sure why that happens, but if it happens to you, I suggest going to your audio pane and switching to the call-in option using the phone number and passcode provided. And if that happens, you can also type that into me and let me know so I can continue to troubleshoot that. Okay, thanks. I would now like to introduce our presenter today. Jeanne Chambers is a research plant ecologist with the USDA Forest Service Rocky Mountain Research Station in Reno, Nevada, and an adjunct professor at the University of Nevada, Reno. Her research focuses on understanding plant species, community and ecosystem responses to environmental changes resulting from disturbance, climate, or invasive species, and in applying this information to problems in restoration ecology. Her current research centers on the uplands and riparian areas of the semi-arid Great Basin. Welcome, Jeanne, and thank you for being here today. Oh, I have to make you the presenter. Just a minor, let's see. Okay, there we go.
All right, can you see my screen?
Yes.
And do I need to minimize the box on the right?
No one else can see it but you, so if it's in your way, then you can. Otherwise, we don't see it.
Okay, great. All right. Well, thanks, Jeanne, and good morning, everyone. I'm very pleased to be part of the Great Basin Science Delivery Webinar Science Series. Most of the work that I'm going to talk about today would really not have been possible without funding from the Joint Fire Sciences Program. My topic, as Jeanne already described, is understanding resistance to invasion and resilience to disturbance, and its importance for restoring and managing Great Basin rangelands. The importance of ecological resistance and resilience to the restoration of disturbed ecosystems has been recognized by restoration ecologists for some time. It's been receiving increasing attention from applied ecologists, especially those focused on climate change issues. Although range scientists really have tended to focus more on state and transition models, they too are looking for methods with which to integrate the two approaches. An understanding of resistance and resilience can help us to take the next step in developing management approaches aimed at restoring and maintaining desirable ecological states in the face of widespread ecosystem change. And today I'm just going to start right out with some definitions of resistance and resilience. And I can't seem to advance, Jeanne.
I know, I was noticing that. If you want, you can
Let me try this.
close back out and see if you can.
There.
Ah, there we go.
Okay. Resilience is the capacity of an ecosystem to regain characteristic processes over time following stress or disturbance. It really is a measure of the recovery potential of an ecosystem. In other words, it is the amount of stress and disturbance that an ecosystem can withstand before shifting to another state. From a management standpoint, there are a couple of components of resilience that are important. These are the amount of time it takes to recover from a disturbance and the amount of energy or effort that it requires to restore an ecosystem to a more desirable state. A related concept is thresholds, and one we're all pretty familiar with. Thresholds are crossed when an ecosystem does not return to the original state via natural processes following disturbance and requires active management to restore. Thresholds are essentially the point where an ecosystem loses its resilience. Resistance is the ability of an ecosystem to maintain characteristic processes despite various stressors or disturbances. Resistance to invasives is of particular importance in the Great Basin. For the purposes of this talk, then, I'm going to use the definition that invasive species ecologists have adopted. This is that resistance to invasives is the biotic and abiotic factors and ecological processes in an ecosystem that limit the population growth of an invading species. Our Great Basin ecosystem types occur over distinct elevation and precipitation gradients, and consequently, they often differ significantly in terms of their ecological resilience and resistance. As we know, they range from salt desert shrub communities at our lowest precipitation and elevation zones through sagebrush, mountain brush and woodland systems, all the way up to forest and even a few remote alpine ecosystems. Two of the major threats facing Great Basin ecosystems, and threats I know that everyone on this call is well aware of, are the invasion of invasive annual grass into our salt desert, sagebrush ecosystems, and more mesic mountain brush and woodland systems. The other, of course, is the expansion of pinyon and juniper trees into our mid to upper elevation sagebrush ecosystems. Today, what I'd like to do is use the work of my collaborators and myself to illustrate the nature of these threats and also the factors that influence ecological resilience and resistance. I'm going to then discuss how this information can be used to restore and manage these systems. The nature of these threats can be well illustrated for our sagebrush ecosystems that are exhibiting pinyon and juniper expansion. Progressive expansion of the competitive trees decreases understory vegetation and, as we know, increases fuel loads. Because of the increase in fuel loads, we're seeing fires of higher severity and also of greater extent, and these are occurring across many areas in the Great Basin. These high severity fires not only kill the trees, as is evident here, but they also kill the fire-intolerant shrubs like sagebrush. Another effect is a decrease in the survival of residual seeds and often plants. The net effect, at least in our lower elevation and more mesic tree-dominated areas, can be decreased resistance to cheatgrass and ecological threshold crossings that ultimately result in conversion to near monocultures of invasive grasses, in this case cheatgrass. Consequences include increased risk to human life and property, high fire management costs, and loss of economic resources. Many of our native species associated with these ecosystems are threatened, and several, like sage grouse and pygmy rabbit, are under consideration for listing under the U.S. Endangered Species Act. In order to restore and maintain sagebrush ecosystems and to reduce the risk of catastrophic fire, fire and fire surrogate treatments are being implemented across much of the region, and I know many of you listening today are involved in these types of treatments. These treatments include prescribed fire, as we can see here, mastication, which involves shredding entire trees and leaving the debris in place, and cutting and leaving the trees in place. Identifying the characteristics of these ecosystems that make them resilient to fire and resistance to cheatgrass can allow us to prioritize vegetation management activities at landscape scales. It also can allow us to implement treatments that will maintain or restore viable sagebrush ecosystems and increase resistance to cheatgrass. These photos are from a successful prescribed fire in central Nevada on the Humboldt-Toiyabe National Forest. This simple graph shows that at landscape scales and for our dominant cold desert shrub types, resilience typically increases over elevation gradients, and those are gradients of available resources and net productivity. More resources and a higher level of productivity by functionally diverse native plant communities effectively increase the capacity of the native community to compete with invaders and regenerate following disturbance. And a good example of this is that our higher elevation sagebrush ecosystems that are dominated by mountain big sagebrush typically will recover more rapidly from fire than our lower elevation Wyoming sage systems, and this is even in the absence of cheatgrass invasion. This graph shows that, again, at landscape scales, ecological resistance to widespread invasives like cheatgrass and also then broadly distributed native species like pinyon and juniper often reflects the ecological amplitude of these species, or in simpler terms, their ability to establish and persist under a given set of environmental conditions. In general, we would expect that resistance to invasives is higher in stressful environments. In other words, our true desert and alpine ecosystems. This is because only a limited suite of species that are adapted to those specific conditions can establish and persist. Salt desert types at the low end of the precipitation gradient in the Great Basin have insufficient available water to support annual grass establishment and reproduction, while if we look at our upper elevation mountain brush types, they often have insufficient degree days or are simply too cold for annual grass growth and reproduction. Of course, the environmental conditions in which salt desert types occur are outside the ecological amplitude of our pinyon and juniper tree species. Historically, as we're all aware, it is our Wyoming sagebrush systems that have been least resistant to cheatgrass. However, as we know, it's now starting to move into our more mesic salt desert shrub systems. Resistance to woodland expansion has historically and still appears to be lowest for our mountain big sagebrush and mountain brush types, and it's highest for our Wyoming sage types, especially when we get into the lower precipitation types. Other factors that we need to consider are those that affect resistance and resilience at local scales, or essentially at the site scale. These include the ecological memory of the site. This includes things like the site potential as indicated by soils and precipitation, the species composition and ecological condition is indicated by native seed banks and seed sources, and also the residual plants and animals, and finally the presence, abundance, and type of invasive species. The severity and frequency of disturbance is also important. This includes things like inappropriate livestock grazing, high intensity fires, and fire return intervals that are less than the historical fire interval. Many of these concepts can be illustrated with the work of my colleagues and myself on the effects of tree expansion and the factors that affect invasion by cheatgrass in our cold desert ecosystems. This first graph essentially is from the Joint Fire Sciences Program demonstration area for examining the effects of prescribed fire on pinyon and juniper ecosystems. Essentially, it shows the mean biomass of the herbaceous species over an elevational gradient that includes Wyoming sage, mountain sage, all the way up to mountain brush communities. And it looks at sites that were either burned or not burned, burn and control, 3 years after the burn. It's important to note here also that these sites had about the same tree cover, 30 to 40%. What this essentially shows, or the first point that I want to make, is that tree expansion occurs across a variety of sagebrush ecological types. Ecosystem productivity, as we already discussed, increases and site potential changes with increasing elevation in systems exhibiting tree expansion. What we saw was that for comparable levels of tree cover, there was a greater increase in herbaceous biomass at higher elevations, and that was both before the burn, which we can see on the control sites, and also then after the burn. We did have a significant increase in the herbaceous vegetation response following the burn and the removal of the trees and the shrubs exactly as you would expect. Because our sites were in relatively good condition before the burn, the perennial grasses and forbs exhibited the greatest increase. What we did see was an increase in our annual forbs following the burn as well, but these were all native species, and we had very little increase in terms of our annual grasses. And this was largely because we chose these sites so that they were in high ecological condition prior to the burn. This particular slide shows the effects of increasing tree cover within the mountain sage community. We're essentially looking at the same experimental design, but this time we're looking at an increase in tree cover that went from 12% to 38%, all the way up to 74%. Here, the ecological memory really decreased. The ecological memory of these sites decreases with increasing tree cover for a given set of environmental conditions. What we saw here was progressively lower perennial grass and forb biomass and higher annual grass and forb biomass with increasing tree density both before and after the burn. And we can see that here again. Here's our control sites with progressively decreasing perennial grasses and forbs. And then following the burn, our lowest tree density site had the highest levels of herbaceous species, followed by the intermediate, and it was lowest for the highest tree density sites. What we did see was a progressively greater increase following the fire in terms of our annual species as tree cover increased. And this again is what we would expect. So in our systems, resistance and resilience were influenced by factors like patchiness, fire severity, and post-fire management. However, in general, what we saw was that resilience and resistance to invasion decreased as tree cover increased. Thus, we can suggest that areas with high tree cover are at risk of crossing ecological thresholds and conversion to cheatgrass or other woody species, as I illustrated in my initial slides. These data are from a companion study at the same location. Essentially, it looked at the same elevation gradient, but also included the effects of herbaceous species removals and fire. This figure shows the number of plants over the same elevation gradient for plots that were either burned or not burned, the controls. What we really see here is that ecological resistance to cheatgrass increased with elevation. The higher elevations and colder soil temperatures resulted in ecophysiological constraints on cheatgrass. Essentially, the highest elevations had the lowest cheatgrass establishment. This was because of colder temperatures, although colder temperatures can result in cheatgrass germination. They often decrease both the growth and reproduction of this species. Site characteristics and growing conditions actually had a greater effect on establishment than either fire or herbaceous removal. And we can see this if we look at this intermediate site. What happened here was that during the cold and wet year, we had lower establishment of cheatgrass. One of the ways in which disturbances like fire and factors that cause depletion of the understory influence resistance to cheatgrass is through resource modifications. These data are from the Joint Fire Sciences Program demonstration area, and they show the effects on available soil nitrogen. Essentially what we saw here was that available soil nitrogen increased significantly after the fire. And you can see this if you compare this burn area with the control area. The effect actually lasted for 3 entire years. What this was a fertilization effect of almost 80 to 100 pounds per acre of available nitrogen. Although other studies have shown that this fertilization effect often occurs after fires, this was the first time it had really been demonstrated that the effect could last for this period of time. This figure shows the increase in resources availability. This figure shows that increases in resource availability can significantly decrease resistance to cheatgrass. Basically, it shows the effects, again, of herbaceous species removals and fires on the biomass and number of plants per seed, number of seeds per plant over our same elevational gradient. And what you're looking at here are plots that we either burned or not burned, our control plots, and in which either 0, 50, or 100% of the herbaceous biomass was removed with an herbicide. Our results showed that the effects of burning and removal on both growth and reproduction were additive. Also, our analyses indicated that we saw or had very similar results across the elevational gradient. Removal alone, and we can see that if we look at our control plots or our plots that were not burned, resulted in a 2- to 3-fold increase in both cheatgrass biomass and number of seeds per plant. Burning, and we can see that if we look at essentially our control plots in which we had no removal and compare that with our burn plots in which there were no removal, resulted in a 2- to 6-fold increase in both cheatgrass biomass and number of seeds per plant. If we looked at the effects of both removal and burning, and we can see this repeatedly here, what we saw was a 10- to 30-fold increase in the biomass and number of seeds per plant of cheatgrass. What this showed was that disturbances that increase resources significantly decrease resistance to cheatgrass, something we were already well aware of, but that really hadn't been quantified in this amount of detail before. It also showed that the mechanism of the decreased resistance is really the growth and reproduction of the individual plants. It doesn't depend on establishment after fire. Another important result from this work was that it showed that the perennial herbaceous species in the system are really critical in terms of increasing the resistance to cheatgrass. We can actually see these same patterns at landscape scales as we see in our small plot studies. This figure shows a structural equation model from a study that looked at factors affecting ecological resilience and resistance and resilience to cheatgrass after a fire at the scale of a watershed. And essentially what we're looking at here is that solar radiation had a positive effect on cheatgrass cover. This essentially confirmed the importance of our lower elevation and warmer sites for cheatgrass growth and reproduction. It also showed that perennial herbaceous grasses and forbs, right here, had a negative effect on cheatgrass cover. So again, this particular slide and this study shows that the influence of perennial herbaceous species is to increase the resistance of cheatgrass, and we can see this even at the scale of a watershed. We also looked at the factors affecting the recovery of sagebrush within the same watershed. This one's a little more complex, but essentially what it shows us is that there was a negative relationship on the pre-burn tree canopy cover with topographic convergence index. So what does that mean? Basically, it showed that the tree cover was highest at our mid to upper elevations. It was lowest at our lower elevations that were dominated by our Wyoming sage sites. It also showed that percent coarse fragments was negatively related with pre-burn tree canopy cover. This was probably an indirect relationship showing that because the trees were not abundant at lower elevation sites where the soils were coarsest, there was a negative relationship with percent coarse fragment and the pre-burn canopy cover of the trees. As you would expect, there was a fairly strong relationship between the pre-burn canopy cover and the cover of sagebrush. Another factor was that herbaceous perennial cover, our grasses and forbs, were positively related with the sagebrush cover. This was somewhat unexpected. What it indicates, though, is that sites with higher cover of native perennial species, or herbaceous species, are more likely to both escape fire and to regenerate after fire at these watershed scales. We can begin to put this all together with this conceptual model. Basically, it shows that the factors that need to be considered when evaluating how the inherent resistance and resilience of a site interact with the characteristics of a disturbance or a land treatment to basically determine whether or not we can meet our restoration objectives. In this particular case, the restoration objectives are to increase the resistance and resilience of the site. Resistance and resilience can be increased by maintaining a desirable proportion of sagebrush, increasing perennial herbaceous vegetation, and decreasing the risk of invasion. To achieve these objectives, the factors that need to be considered are first, those that influence the environmental conditions of the site, and in other words, essentially determine the ecological site type. These include topography, elevation, slope, and aspect, the abiotic environment, the long-term precipitation, the temperature regime, the soil type and depth, and also factors that influence soil water and available nutrients, like soil textures and then also organic matter. The factors that affect the ecological condition also need to be evaluated. And in sticking with our pinyon and juniper expansion story, these then include the pinyon and juniper cover and also age of the trees. Another factor that needs to be considered in terms of ecological condition is the past and present livestock grazing, both the duration and the intensity. Of course, the understory species composition is a critical element because it largely determines the recovery potential of these sites. It includes the sagebrush type and cover, the perennial herbaceous cover and diversity, and also the cover and diversity of the invasives of the site. We can't neglect the disturbance and treatment characteristics, especially when we're working at landscape scales. We need to consider the size, shape, and intensity of these treatments. And finally, in our arid systems, we also need to be very aware of post-treatment precipitation. It really is only by assessing all of these factors that we can be assured of obtaining our desired objectives of increasing the resistance and resilience of these particular sites. With that as a background then, a basic approach for managing and restore these ecosystems using the concept of resistance and resilience includes, first of all, assessing the environmental characteristics, vegetation types, and ecological conditions at landscape scales. Most management plans now encompass landscapes with multiple project areas. Understanding how individual projects affect future fire behavior, livestock use patterns, and wildlife movement are critical for maintaining resilient ecosystems. Second, it is to develop an understanding of ecological resistance and resilience and the relationships to thresholds for the ecosystems of interest. Another Joint Fire Sciences Program sponsored project, the Sagebrush Step of Treatment Evaluation Project, is helping to increase our understanding of ecological thresholds for sagebrush ecosystems exhibiting either cheatgrass invasion or pinyon and juniper expansion. It is basically quantifying the factors that determine ecological resistance and resilience, including many of those that we've already talked about today. Another thing it is doing is to evaluate the effectiveness of common management treatments. These include prescribed fire, cut and fell, herbicides, and mowing. You can learn more about these projects and the overall effort of the SAGE STEP group by Googling or just going directly to sagestep.org. The third aspect is to prioritize management activities at landscape scales. The categories include protection, prevention, and restoration/rehabilitation. Protection involves protecting areas with inherently low resistance or resilience, like our lower elevation salt desert and Wyoming sage types. It also includes protecting areas of high conservation value and areas at risk of crossing ecological thresholds. The focus here is primarily on eliminating stressors like repeated fire and inappropriate livestock grazing, controlling surface disturbances and invasion corridors, and also increasing efforts to detect and eradicate exotic species at the early stages of invasion. Preventative management involves maintaining or increasing resistance and resilience in areas that have declining ecological conditions or that are in the initial stages of cheatgrass invasion or tree expansion. Eliminating stressors is still a high priority here. The focus really should be on areas with higher inherent resilience. Objectives are those that we already discussed: increasing herbaceous perennials through competitive release from shrubs and trees, and reducing woody fuel loads to minimize the risk of high severity fire. We've also already discussed the types of treatments we can use. In this particular scheme, restoring or rehabilitating areas that have crossed thresholds is of lower priority. This is really because, or this can be well, I think, described if we look at the example of areas that are currently dominated by cheatgrass or medusa head. These areas, especially the lower precipitation zone sites that have already been converted to annual grasses, are both challenging to restore and the costs are often prohibitive. A better strategy really is to use protective and preventative management to maintain our intact areas, of course, while we continue to work on developing that silver bullet for annual grass-dominated areas. This is a strategy that has been advocated by the BLM-sponsored Great Basin Restoration Initiative. Exceptions to rehabilitation and restoration include the BLM Emergency Stabilization and Rehabilitation Treatments and the burn area emergency rehabilitation seeding that is conducted by the Forest Service. Oftentimes our best opportunity for preventing conversion to annual grasses is immediately following the first time a system burns that is still dominated by sagebrush. It is important to note, however, that this type of seeding is not necessary in areas with adequate perennial grasses and forbs. In fact, it can hinder natural successional processes and alter species composition. Other areas that deserve consideration for restoring and rehabilitating include areas adjacent to intact vegetation communities that can serve as buffers or fire breaks, the wildland-urban interface, endangered ecosystems, and critical habitat for T&E species. Another factor that we should consider is that restoration or rehabilitation seeding really does offer an opportunity to increase both resilience and resistance of many of our sagebrush ecosystems. Seeding species that differ in life form, rooting depth, and phenology can have multiple benefits. This includes higher resource use and increased competition with invaders, a greater capacity of these communities to persist following disturbances that result in mortality of vulnerable species. And an example here might be the arugula moth and its effects on sagebrush mortality. Structural diversity can also be increased, and as we know, this is necessary to support many of our sagebrush obligate species. Another factor to consider is that seeding species that are adapted to a changing climate can help prevent surprises. For the Great Basin, the predictions are for a warmer and drier climate. This indicates that we should be looking at species that are adapted to more xeric conditions, or at least looking at those species that occur at the drier end of the ecological site types with which we are working. I really wanted to conclude with a case study of how we can apply resilience and resistance concepts at landscape scales. This particular one focuses on a Forest Service planning unit that includes the Northern Monitor Range in central Nevada. Here we're looking at a precipitation gradient that ranges from about 10 inches at the lower end, or 6,000 feet in elevation, to almost 18 inches at the upper elevations, which are at about 8,500 feet. Vegetation on these sites range from black sagebrush and Wyoming sagebrush types at the lower elevations, mountain sagebrush at the intermediate elevations, all the way up to mountain sagebrush and mountain brush at the upper elevation. The management objectives are, as we've already discussed, to increase resistance and resilience. We can do this by maintaining a desirable proportion of sagebrush on the landscape, increasing perennial grasses and forbs, and decreasing the risk of invasion. As you should expect by now, The different vegetation types in this planting area vary in both resilience and resistance. For our black sagebrush and Wyoming sagebrush types, we are looking at relatively low elevations. Precipitation and productivity is also moderately low. The ecological condition on these sites, however, is fair to good. The abundance of invasives is that cheatgrass is present and it's locally abundant. This is a vacant grazing allotment and has been for some time. The management implications are that we would expect slower recovery due to the low productivity on these sites. We also, because of our low elevation and the fact that we are really in the Wyoming sagebrush zone, would result in higher risk of cheatgrass spread, especially after fire. These particular sites have a lack of fine fuels. This is another consideration because it indicates that prescribed fire is really not a viable option for these systems. That, coupled with the high risk of cheatgrass invasion, indicates that mechanical treatments are probably the best option. We would want to minimize surface disturbance in these areas, and we'd also, of course, want to manage grazing. Our past experience on burned areas indicates that even a single year of excessive grazing can result in conversion to weed dominance. If we look at our mountain sagebrush type, we really are in the woodland zone. The elevation is intermediate. The precipitation and productivity of these sites is moderate. The ecological condition, however, is fair to low. This is because we're looking at high tree densities and fairly high fuel loads. A lot of the area is in phase 2 to phase 3 woodland condition. It also has depleted understories and low abundances of our perennial herbaceous species. The abundance of invasives is that cheatgrass is present and locally abundant, and that this is an active grazing allotment. Implications here are that we would expect low recovery due to the high tree cover and also the depleted understory. There's higher risk of cheatgrass spread, especially on the south-facing slopes, and there's higher risk of severe fires. The implications in terms of management options are that these areas should only be treated where they have low tree abundance, and that the preferable method would probably be our mechanical methods, either cut and leave or mastication. Other options include creating fuel breaks so that when wildfires do burn through these areas, the extent is decreased. And another important consideration is that following fire in these areas, it is necessary to revegetate if we want to return these systems to the native community or even to stabilize these sites. Of course, we again would want to manage grazing after treatment. If we move on to the mountain sagebrush and mountain brush types, we're at our highest elevations. Some of these are at 8,000 to almost 8,500 feet. Precipitation and productivity is moderately high. The ecological condition of these sites is good. There are low densities of trees, generally only phase 1, and there are abundant perennial herbaceous species. The abundance of invasives, as you might expect, cheatgrass is largely absent because of the colder temperatures at these higher elevations. This is, however, an active grazing allotment. Management implications are that we would expect higher recovery rates, a lower risk of cheatgrass spread at these high elevations, and also because of the low tree densities and relatively low fuel loads, a lower risk of severe fire. The management options are to treat with prescribed fire. This has worked quite successfully in these higher elevation systems before and should probably work well in this system as well. Again, we would want to manage grazing. A caveat for all of these sites is that we would definitely want to monitor the results for as long as 5 to maybe even 10 years after treatment. We'd use these results then, of course, to adapt our management. Things like adjusting livestock grazing and certainly proactive control of any new populations of invasive species that occurred on these sites. I always like to conclude by looking at the road forward. As we know, our Great Basin ecosystems are undergoing rapid, large-scale, and often undesirable changes. Prioritizing restoration and management activities based on resistance and resilience may be an important step to increasing their sustainability, maintaining ecosystem services, providing for species of concern, and, looming on the horizon, adapting to a changing climate. I wanted to acknowledge all of those individuals who have either contributed to these studies or have contributed to these ideas. And with that, I'll turn it back over to you, Janie.
Thank you, Jeanne. All right, I will now field questions. So if you have questions for Jeanne Chambers, please type your questions in your question pane, and I will do my best to pronounce your name correctly. We need some hold music. Well, Jeanne, I guess you did such a good job. You have answered everyone's management questions.
Either that or confounded them. I'm not sure which.
Okay, here we go. The first question is from Heather Lintz. She asks, where is grazing most often occurring? What type of system?
Hello, Heather. As a researcher, I may not be the best person to answer that. I have worked, I guess, on several different BLM districts and then also on the Forest Service districts. So in terms of an environmental gradient or an elevational gradient, grazing occurs at all different elevations. It really depends on the permittees and their needs at the time, and also then I think the decisions of the land managers as to which grazing allotments are currently active versus those that are not. I'm not sure that that adequately answers your question.
Well, if you, Heather, if you want to follow up, you can type in a follow-up question and I will get to it. Okay, thanks, Jeanne. The next question is from Louisa Evers. She says, many of the concepts discussed here are similar to the FRCC concepts. Have you looked into how to incorporate the two?
I have looked at several different management schemes that are currently being used, and there are several that try to incorporate these systems, these particular concepts, and these specific terms and how they're being applied. Like I said, they're being included in state and transition models, and I know that David Brisky and also Tamsin Stringham have been working on those particular concepts. Work by Louis Provencher has tried to also incorporate at least the ideas for the FRCC types of ideas. If you would like to discuss this in more detail, I would be happy to visit with you.
Great, thank you. Next question is from Cheryl Mandich. When is the landscape level controls on Bromus tectorum expected to be in print, and in what journal?
The landscape level controls are really already in print. There was an ecological monograph in 2007, and I was the lead author on it. It actually includes much of the data on cheatgrass, or all of the data on cheatgrass that I described today, plus a lot more.
Okay, thanks. Tina Knapp asks, how does this information apply to wild horses, or are horses included in grazing management?
I believe that horses would necessarily have to be included in grazing management. They have similar and in some cases even greater effects on ecosystem recovery than do cows and other livestock.
Okay, thank you. Lee Turner asks, on sites where there is relatively high perennial understory cover correlated with sagebrush, what management opportunities might help us promote continued high perennial cover?
I think probably our best option here is simply to monitor these sites over time. If we start to see changes in ecological conditions, then we might want to consider going in and doing some type of treatment. Otherwise, they are probably best left alone.
Okay, thank you. Margaret Horner asks, oh sorry, it shifted for a second. What was the intensity of fire used or present in the Rao et al. Study, which found an increase in soil nitrogen post-fire?
That was a prescribed fire in underdown drainage. It was part of the Joint Fire Sciences Program demonstration area on looking at the effects of prescribed fire in pinyon and juniper dominated watersheds. And basically the intensity of fire would have been relatively low. Those were mostly spring burns, and fire temperatures and soil temperatures again were relatively low. We have those data. If you're interested in them, I'd be happy to share.
Thank you.
And in fact, you can look up the Rao et al. Manuscript. I know that Ben has those temperatures in that particular manuscript. It's Rao et al. 2007, Fire in the Great Basin and Effects on Nutrients. He has several of them. Please email me if you would like more details on either those manuscripts or the soil temperatures that were associated with the burns.
Thanks. And as a follow-up to that, I know some of you in government agencies have a hard time getting PDFs, but for those of us that are housed at universities, you know, that's a little bit easier for us, so we can always send you PDFs if you need help with that. Just email us. Okay, next question from Sherry Howell. Is there a location where we can view the PowerPoint for future reference? Oh, I can answer that. Yes, the GoToWebinar system will automatically send you the video link tomorrow, and then I will also post this on our website so you can view it in the future as well. Okay, there's a question from Cheryl Mandich again. What is SRCC? Oh, FRCC. I actually had that question too. Louisa asked about the FRCC. What is that, Jeanne?
I think we'd have to ask Louisa. I'm familiar with it, but I don't know that I could correctly provide the full terminology for the acronym.
All right. Well, Louisa, if you wouldn't mind. Oh, here she goes. Louisa typed in, it's Fire Regime Condition Class. Is that through the Forest Service then, or the BLM, I mean? All right, let me get to the next question. Ryan Niemeyer asks, which ecological community species are projected to be more resilient for increased temperature and drought?
That's an excellent question, and one that I'm not sure that we really understand at this point in time. What we would expect, perhaps, is that some of our lower elevation and more arid systems would be the least resilient. An excellent example of this is perhaps Bethany Bradley's paper, in which she looked at the increases of temperature in an area just outside of Ely, Nevada, and what the effects might be on those systems. What she found was that temperatures could increase to the degree that not even cheatgrass would actually be able to survive and persist on those sites, and that we might see these sites transition to more the Mojave type condition. However, we may also be looking at novel communities, community types or situations that we really have not seen in the past.
Okay, thank you. Brad Jessup asks, is there a resiliency guideline as far as perennial plants density and or cover are concerned? In other words, is there a guideline like 2 to 4 deep-rooted perennials per meter squared equals resiliency?
The only one that I know of that people have actually tried to do that are those that Rick Miller has come up with, and that is more for the northern western juniper systems. And they believe that plants of about 1 per meter squared, 1 perennial deep-rooted species per meter squared, would allow those systems to recover following fire. However, what we have to consider is that as we go across these elevational gradients, we would expect that those numbers and those covers would change considerably. We may have some fairly good data coming pretty soon from the Joint Fire Sciences sponsored project, the SAGE STEP project. And what it could do is give us an indication, at least for the sites that were studied, what levels of perennial herbaceous species resulted in adequate recovery of those particular sites.
Thank you. Kimberly O'Connor asks, under what conditions would cut and leave be favored over mastication? Does mastication alter composition of native herbs and grasses unfavorably in the system studied?
To date, I don't believe we have enough data on mastication treatments and their long-term effects on either soil nutrients or plant species composition to be able to state what the longer-term effects are going to be. Hopefully those data will be forthcoming.
Great. As a follow-up to the question about what FRCC stood for, the Fire Regime Condition Class is an interagency term that came out of the Land Fire Project. Louisa Evers says fuels projects and all the federal agencies are required to assess the impact on FRCC. So thanks, Louisa. Okay, next question from Stan Kitchen. For higher elevation forested sites, what kinds of treatment strategies do you propose that reconcile historic fire regimes, moderate to high frequency, mixed severity, and forest structures with current stand conditions and restoration needs?
I'm not sure if you're talking about woodland sites or forest sites, Stan. In terms of woodland sites, of course, we would want to be very aware of where we had our older, more persistent pinyon and juniper systems. And we would want to try to identify those prior to any treatment and to avoid either burning them or actually doing any kind of mechanical treatment in them.
Okay, thanks. If you have a follow-up to that, Stan, you're welcome to type it in. Alex Suazo asks how to promote resilience and resistance in areas burned by wildfires.
I guess it depends on if we're talking about before burning or after burning. If they've already been burned by a wildfire, we need to assess what the residual perennial herbaceous component is. If there is a significant perennial herbaceous component, and if we're at relatively high elevations and higher precipitation zones, then perhaps we would not want to do anything but allow natural recovery. We could promote resistance and resilience by decreasing any additional external stressors to those sites, deferring grazing and then only moderate grazing after we begin to regraze those sites. If we're at lower elevations perhaps, and we know that we already have very low perennial herbaceous species, then we can perhaps increase the resistance and resilience of those sites by seeding with a diverse species complement. The problem here, as we're all very aware, is that at our lower elevation systems it's often very difficult to establish native species.
Okay, thank you. Heather Lentz asks, how does grazing intensity interact with disturbance and fire on system recovery?
That's also a good question, and one I don't believe, again, that we have enough data for. I think it's an area that deserves additional study, especially for a lot of our systems. I think a lot of what we could conjecture, or at least draw from past studies, is that we would expect that more intense fires are going to result in lower perennial herbaceous species afterwards, and consequently they will provide less forage. I guess if we go full circle on this, grazing of those sites then might have a greater impact in terms of decreasing the rate of recovery.
Okay, thank you. Sherry Howell asks, are there studies anywhere to see if mastication in place results in greater soil carbon?
Work has been done by Ben Rao and Dale Johnson on the effects of mastication. I'm not sure that they have published that yet, but we could certainly email either Ben or Dale and find out. Another study that I know is nearing conclusion is one that Bruce Roundy is doing with one of his graduate students. I believe that that one is nearing completion as well.
Thank you. Cheryl Mandich asks, how long does it take for fungi to come back after fire? In parentheses it says, in regards to Wyoming sagebrush establishment.
That's a good question and one I'm really not prepared to answer.
Okay, we'll try to get back to you with that one. All right, Stan Kitchen asks, in follow-up to his previous question, I'm asking about forested sites with ponderosa pine, firs, or 5-needle pines, many of which, but certainly not all, have secondary post-logging tree cohorts. Did you want me to read the first question again, Jeanne?
Yes, please.
For higher elevation forested sites, what kinds of treatment strategies do you propose that reconcile historic fire regimes, moderate to high frequency and mixed severity, and forest structures with current stand conditions and restoration needs?
Well, I'd have to answer that Stan probably knows more about that than me. And that since I have not worked in those systems, I would probably defer to him.
Okay. All right. Are there any more questions? All right, well that looks like it. If you have more questions later, please email me or Jeanne and we'll do our best to get back to you in a timely manner. We look forward to bringing back our webinar series in the fall. If you have ideas for webinar topics you would like to see discussed, or if you are in need of an expert to visit your field site this summer, or if you have any other information needs that I can help with, please email or call me. Thank you very much, Jeanne, for your presentation today, and thank you all for your participation. Okay, thanks, Jeanne.
Thank you.